Have you ever really thought about how you describe a trip? You say where you started, how far you went, maybe how fast you were going. Well, physics has a super precise language for all of that. It's a framework that turns those kinds of vague ideas into really sharp analytical tools. And today, we're going to master that language. So let's dive right in.
Look, whether you're crawling in traffic, sprinting to catch a train, or just taking a walk down the street, you're in motion. But how do we actually describe that motion like a scientist would? How do we go from just saying something is moving to a precise mathematical description that lets us, predict and analyze it?
Before we can even begin to talk about moving, we have to agree on something really, really fundamental. Where are we starting from? It sounds almost too simple, right? But trust me, this is the absolute bedrock of everything else we're about to build.
If I just said, I'm 2 meters away, that's totally meaningless. 2 meters away from what? And which way? See, to give any location real meaning, you need two things. A starting point, we call that the origin, and a set of directions, like forwards and backwards or left and right. Put those together and you've got what's called a frame of reference.
Think of it like one of those "you are here" signs you see at a mall. That sign? That's your origin, your reference point, and the map itself gives you all the directions. Without that frame of reference, that map is just, well, a bunch of useless lines. But with it, you can figure out how to get anywhere.
So once we have our frame of reference locked in, then we can define our position. It's really just your specific location measured from that origin point. We usually give it the label x, and in the world of physics, we measure it in meters.
And this right here makes the whole idea of position perfectly clear. If we just decide that Cosmo's house is our origin, our 0 point, then we can define every other spot relative to it. So the shop is at positive 200 meters and the school is at negative 300. And this shows you that the plus or minus sign isn't just about the number, it's telling you the direction. Okay, so we've figured out how to define a location. Now let's get moving. But this brings up a really, really important distinction. Is the path you take the same as your overall change in location? Well, physics has a very clear answer. Nope.
First up, we've got distance. This is the one you're probably most familiar with. It's simply the total ground you covered. The best way to think about it is like the odometer in your car. If you walk along this squiggly path, the distance is the full length of that dashed line. We call it a scalar, which is just a fancy way of saying it's a number that doesn't have a direction. Like 5 kilometers.
Now let's compare that with displacement. Displacement could not care less about that winding path you took. It only cares about two things, where you started and where you ended up. It's a straight line change in position from start to finish. And this visual is perfect because it shows you why displacement is a vector. It has a magnitude, that's the how far, and a direction, which is shown by that arrow. So let's put them side by side to make it crystal clear. Distance depends on the path you take. Displacement doesn't. Distance is a scalar. Displacement is a vector. And because of that, displacement is always a positive number. You can't unwalk miles on your car's odometer, but displacement, that can be positive or negative, all depending on your direction from that starting point. All right, time for a little pop quiz, just to see if this is clicking. So get this. Kevin walks 500 meters from his house to the shop. Then he turns around and walks the same 500 meters right back home. Now his total distance is pretty obviously 1,000 meters. But what's his displacement? 0. That's it. It's 0. Why? Because displacement only cares about the start and end points. And since Kevin ended up in the exact same spot where he started, his overall change in position is 0. As far as displacement is concerned, he's gone absolutely nowhere.
So, we can now tell the difference between the journey and the destination. Now things get really interesting, because we're going to add time into the mix. This gives us two more super important and often confused ideas, speed and velocity.
So average speed is pretty much exactly what you think it is. You just take the total distance you traveled, remember that's your odometer reading, and you divide it by how long the trip took. It's a scalar, just like distance was. It tells you how fast you were going but gives you 0 clues about which direction.
Average velocity, on the other hand, is built on displacement. It's your change in position divided by the time it took to make that change. And because it's built on displacement, that means it has to be a vector too. So it doesn't just tell you how fast, it tells you how fast and in what direction. So you see the pattern here, right? It's actually really simple and kind of elegant. Distance gives you speed. Displacement gives you velocity. The first pair, those are your scalars, just telling you how much.
The second pair, those are your vectors, telling you how much and which way.
So far we've covered position and, well, moving at a pretty steady rate. But what happens when things change? You know, when you hit the gas pedal or slam on the brakes. For that, we need our final big deal concept, acceleration.
In everyday life, we usually think acceleration just means speeding up. But in physics, it's so much more than that. Acceleration is any change in velocity. And since velocity includes both speed and direction, you can accelerate by speeding up, slowing down, or even just by changing your direction.
Now check out the arrows here, because this is key. If your velocity and your acceleration are pointing in the same direction, you're speeding up. Simple, right? They're working together. But if your acceleration points in the opposite direction of your velocity, you're slowing down. The acceleration is literally fighting against your motion. This shows you a really important point. Negative acceleration doesn't always mean slowing down. It just means you're accelerating in the negative direction.
Position, displacement, velocity, acceleration, we've just built a complete toolkit for describing motion in a straight line. Now, let's put it all together and see how physicists use these tools to understand the entire story of a journey in a single glance.
Okay, this might look a little complicated at first, but trust me, these graphs are the big payoff for everything we just learned. By plotting position, velocity, and acceleration over time, we get this complete visual story. A flat line on the position graph? That means you're just standing still. A straight slope line? That's constant velocity. And a curve? That means you're accelerating. These three graphs, this is the language of motion made visible. So here's the big takeaway. You now have the fundamental vocabulary to describe pretty much any journey you see, from a single leaf falling from a tree to a rocket launching into space. You can tell the difference between the path taken and the destination reached, how fast you're going versus which way you're headed. So the next time you're in a car, just think about it for a second. What's your velocity? And when you hit the brakes, which way is your acceleration pointing? What motion around you will you never see the same way again?